We'll start off with a keynote by Chris Wyman, Traveling the Path of Reuse. It's on ReSTIR. Chris is a distinguished research scientist at NVIDIA and has been there for quite a few years, working on real-time ray tracing, path tracing, and so on. And yeah, we'll hear more about this in the talk now. So.
All right, thanks. I'm going to pace, so I need a mobile device. All right, so I was asked today to talk about ReSTIR. And so for those of you who don't know what ReSTIR is, I'll talk a little bit about that as we get going. But because it's sort of a mixed audience, and I've done a lot of deep dives elsewhere, I thought maybe it was a time to take a step back and think about the takeaways that we've gotten from the work that we've done with ReSTIR over the past 5 years. Also, I mean, there's a lot of you who are students here, and I want to talk a little bit about how ReSTIR came about, because at this point it's fairly well known, at least within the rendering side of graphics, but it wasn't planned. It was a total accident that we discovered ReSTIR, and I actually think that's a little bit inspiring for those of you who are students who are like, what's my big impact going to be? That you can actually stumble upon something and literally trip on it, and that it turns out to be a really big thing. And so hopefully by walking through how we discovered this will help you get inspired that you can do that too. And also, one of the things that I want to talk about, the one slide I have notes on. So I'm going to talk a little bit about the algorithm and our research, a little bit about why we developed ReSTIR and how we've developed and why we've developed it in the way we have. A little bit about industrial research and the challenges that brings, and then where we are thinking about moving forward. Now, one thing I do want to note is a number of academics have at various times said, we don't want to work on ReSTIR because we can't keep up with you guys. And what I want to point out is this is not a competition. My job is not to keep ahead of everyone else in the research community. My job is to inspire people to do work that's beneficial for NVIDIA and the graphics community. And so I don't want to compete with you. I want to collaborate with you. And so if you have ideas on ReSTIR and rendering, come talk to us. We collaborate pretty well. And in fact, I want to start off by saying that what I'm going to talk about in this talk is not just my work. This is the work of many people I've been collaborating with. And really, it's a large list. And I want to start off by just saying my primary research collaborators have been Marcus Kettinen and Dachi Lin. And what I mean by this is if you see any good ideas in this talk, they're probably theirs. And if there's any bad ideas, they're probably mine. But I've also collaborated with a bunch of other people. They're sort of organized loosely by a number of former interns of mine or current interns. Full-timers at NVIDIA, faculty out in academia. But then it's also important to realize that we start to productize things, and there's engineers on the product side who do amazing work and contribute amazing amounts of information and direction to the research. And so there's a number of them here who have worked on RTXDI, integration into games and engines, help on denoising, help on art to help us look at real assets and evaluate things. And very importantly as well, management. If there wasn't support from the management across NVIDIA, we couldn't have built this collaboration. And so this is really important to note for those of you who are students. Big projects are not just the work of one or two researchers, they're huge collaborations. All right, so let's talk about ReSTIR a little bit and why you should care. And let's talk about that by looking at this image. So this is a fairly complicated scene. All the light arrives from beyond a double pane set of windows. And so there's glass. All the light comes through glass here. There's a number of highly specular surfaces. There's fine subpixel detail. There's multi-bounce global illumination, back behind in these sort of shadows, beyond the fact that this is all acoustic, right? There's multi-bounce GI beyond that. There's extreme depth of field, so the nearby plant almost looks transparent, or actually is transparent. And there's fine geometric detail on the floor that's kind of weird. I can't really describe it beyond weird. So how does ReSTIR render this? So to start with, this is a million pixel or a million sample per pixel reference image. So it's just naive path tracing run to the extreme. And this is what it looks like with ReSTIR in 15 milliseconds on RTX 5090. And so I can go back and forth a few times here. And so it's certainly not nearly the quality of the million sample per pixel, but for 15 milliseconds, something that you could actually run interactively. Sure, it's high-end 5090, but at least you could, conceive of doing this in real time in a real application. And then this compares against a one sample per pixel naive path tracer in 5 milliseconds on the same hardware. So that's what ReSTIR is, and what it's about is trying to get these very, very complex lighting transport in real time. All right, so what is ReSTIR exactly if you haven't heard about it? Well, ReSTIR is reservoir-based spatial temporal importance resampling. And the key idea here, and this is really what I want to emphasize and get back to, is it's amortizing the cost of samples. It's doing reuse, sample reuse, and this reuse is happening from neighbors both spatially and temporally. And the key thing here is not just reuse, which is very important, but the key thing is it's got an efficient streaming implementation. And if you've never heard about reservoir sampling, and I was in that category 5 years ago, you should know the algorithm reservoir sampling. It's very important. It lets you reuse a bucket of, an infinite number of samples without storing them all, which I think is kind of magical. And this is part of what allows ReSTIR to do what it's able to do today, is you can do this really cool streaming implementation of sample reuse without storing all of the samples that you're reusing at every pixel. And this is kind of magical. And so why? Why do we need this? Well, if you think back to 2018 when NVIDIA launched hardware accelerated ray tracing in our GPUs, the best GPU could budget somewhere on the order of 1 ray per pixel at realistic frame rates. And so, for instance, I had a bunch of DXR tutorials a number of years ago, and I sort of circled and blew up. It was 25 or 27 frames per second, and this basically had two rays, one shadow ray and one bounce ray. So it was pretty limited. And even today, you go to high-end games, and one path per pixel can sort of bring top GPUs to their knees once you put that within the context of a sophisticated game engine. And so really, the point here is we must amortize costs if we're going to increase this quality and the fidelity and the amount of complexity in our lighting scenarios. And so that's what ReSTIR is aiming to solve, or that's what I'm aiming to solve with ReSTIR. And then what happens from this is you pass this to a denoiser usually, but denoisers reuse the final pixel color, which is really cool. But if you think about it, when you're reusing the pixel color, you're throwing away a lot of information that you computed along the path. All the bounces, all of the lights that you connected to, all you have is this radiance value, or maybe a radiance value. You have this final color, and you've thrown away everything else. And so modern denoisers are starting to add that data back in. They find it's valuable. And so they start attaching a G buffer with position and normal and distance to reflection, things like that are valuable for the denoiser. Kind of what ReSTIR is saying is, why throw it away in the first place and then have to add it back in? Why not just keep it around and reuse it while you have it? And so you could sort of view ReSTIR as a denoiser of PDFs, probability distributions, which is another interesting thing to think about. So why do we need this? Why is ReSTIR needed? And I didn't go through this thinking when I designed it. I tripped over it. But there's a lot of techniques that have been reusing samples for a long time. So I don't want to pretend that this is the first approach that reuses lighting. There's irradiance volumes, irradiance caches, PRT, instant radiosity, bidirectional paths, metropolis, all these sorts of things. And there are issues. If you want to step back and look at these, they all have limitations of various kinds. PRT is pre-computed, so that limits you if you've got dynamicism. Some things are known to be tricky to implement. I mean, bidirectional and Metropolis, people often avoid them just because they're so tricky. I have a thing about data structures. If you keep adding data structures and you have to update them every frame, that's a limitation because that's a lot of traffic to and from memory to update things. They're also coarsely sampled, so they limit these things, these caches. They limit the frequency with which you can reconstruct. Some techniques have singularities, some instant radiosity techniques have singularities. And actually, Beckert et al. Is one of the closest to ReSTIR, but it wasn't really developed particularly well. And so you can sort of think of ReSTIR as sort of a derivative of Beckert et al. Path reuse. All right. So how did ReSTIR come about? Well, I don't think I'm kicking anything. How did ReSTIR come about? And this is the part I hope is inspiring for those of you who are more junior researchers who are thinking about how to come up with problems on your own. So prior to the launch of our RTX cards, we knew ray tracing was going to be a big deal. I mean, we knew it was coming internally, so we were thinking about it and trying to figure out what these things would be good for. And so we started asking what prevents real-time ray tracing in games today, and what should gamers want from ray tracing? Why would they want it? And I sort of saw ray tracing as this huge research opportunity, because if you think about game developers and the algorithms that they use, they rely on all these things that are affectionately known by as ReSTIR hacks, and they use them to improve speed and quality, but there were no ray tracing hacks. And so I thought, if we have this ray tracing, people should really come up with all these ray tracing hacks that are actually what's going to be used in games. And I thought this was a huge opportunity because no one had done that. And the reason no one had done it was the prior ray tracing research was largely focused on offline. People were saying, all right, ray tracing and path tracing is great for film rendering, but no one's ever going to use it for real time. But when you come to real time, the constraints change. You have 3 million X less compute per frame than a film renderer. And this number's probably changed from when I heard that from someone else. But that is a huge change in the constraints, that you have a 3 million X difference in your budget per frame. And that changes what algorithms you want to use. You don't want to use the same algorithms when you have this huge difference in constraints. So we started thinking about what's going to be necessary for ray tracing in games, and denoising was clearly an issue. We knew 1 sample per pixel would sort of be our initial max ray budget. And so we focused on some things like denoising, and I was involved in a couple of these, not as a primary researcher, but denoising like SVGF turned out to be important. But after sort of thinking about this and pushing people to say, hey, why don't we try some ray tracing hacks? I realized I actually had some ideas. And so, but to get there, I thought, why should ray tracing matter to gamers? This is an interesting question. And it's an interesting question to ask about your own research, because what matters to you as a researcher is different from what matters to developers, which is different than what matters to gamers. And so this is important to think about. And so we started listing some obvious ray tracing capabilities at 1 sample per pixel, exact dark shadows, for instance, or correct stochastic soft shadows. And I started getting worried because it wasn't clear to me that these were going to be what gamers cared about. I care about them quite a lot, but I wasn't sure if gamers would. And some of that is that there were some ReSTIR hacks that people came up with, including some that I'd come up with over the years, that no one really used. They were cool. They would solve some of these problems, but they weren't used. And so if we came up with something else that was expensive, that was hard to integrate into a game, would people use it? And so I started asking, can we add something new? Not that these are not valuable, they are, but I was worried that people wouldn't value them enough to pay their money. So can we add something new? And so what we did, or what some of us did, is we started rendering a bunch of scenes. We went and gathered as many scenes as we could and started rendering them with a naive ray tracer, path tracer. And we started to see some scenes like this that stood out and looked different than what we saw in games. And this stands out because there were hundreds or thousands of these mesh lights scattered around the scene. They had view-dependent shadows. This scene, well, in particular, because there's a little bit of specular, has both diffuse and specular shadows. And I had never really thought much about specular shadows. But when you start to see them and they move and interact with you as you move around the scene, they're really cool to get both diffuse and specular shadows from the same object. And then in the shadows is mostly direct lighting. So this particular scene is lit by a large number of outdoor lights. And because it's so well lit, global illumination isn't really a big deal. If you render this without GI, it looks mostly the same as with GI. And so you don't actually need a lot of bounces and path tracing in this particular scene to make it look good. And so that's also good for, you know, if we have 1 or 2 rays per pixel, what can we do that looks new and is cool? So then, this is what it looks like without shadows. So you switch back and forth, and this is what ray tracing gives you in this scene, and that's a huge difference. And maybe that's something someone would care about and pay for. And so that's sort of where we got to, well, maybe mini lights is the thing that we need to solve. All right, so then the first thing I did was I said, all right, I don't have the rays to do this. I don't know how am I gonna sample hundreds or millions of lights? I'm gonna have a really noisy signal. I'm gonna need a good denoiser for this. Let's build a denoiser that can reconstruct this. So this is some early experiments that I was working on where I stumbled upon ReSTIR. And so on the left side, I had my input 1 sample per pixel lighting for this scene. It was pretty naive lighting, but you know, it was 1 sample per pixel. And I was denoising it into this thing on the right. And so objectively, this is a huge improvement in the denoiser. Subjectively, it's not useful at all. So if you look at this denoised result, it's not much better than a light map. In fact, it's probably worse than a light map. It doesn't change very nicely. It blurs a lot. It loses a lot of detail. And so if you look at the A-B comparison between them, it's a huge improvement. And then if you go talk to anyone, they're going to say, this isn't useful. I don't want that. Go away. And so I thought, well, maybe the denoising problem is too hard here. So maybe I better have some better input samples, and then I can denoise it better. And so I asked, well, how can I get some better samples here? And we had a couple algorithms that would allow us to do that, but they were going to take me like weeks or a month to integrate into my code. And I said, hang on, I've got a simple idea. I think I'll use that to get better samples. It was going to take me 5 minutes, really simple idea. Here it is, 6 years later, I'm still working on it. So that's sort of karma for you. I thought I'm going to use this simple thing that's only going to take me 5 minutes rather than this thing that's going to take me a couple weeks, and it's instead taken me better part of a decade. So what was this simple idea? So if you have a scene with a lot of lights, you're going to pick one randomly, for instance. And maybe you're going to pick this one that's in the negative hemisphere. There's no reason to trace a ray to that light. You already know in advance it's beneath your horizon, it's in shadow, it's not going to contribute, so why trace a ray? It's a waste. But you'd kind of like to trace 1 ray for every pixel for coherence reasons. You don't want to have your pixels diverge. Wouldn't it be nice if you could not have a black pixel there, but pick another light so that you could get a lighting sample in every pixel? So maybe you randomly pick again, and because you randomly pick again, you might also pick one in the negative hemisphere. So you keep trying until you get a light that's in the positive hemisphere, and then you trace a ray. So if you're going to trace 1 ray per pixel, it should at least be to a light that might actually be visible. And so this was the key idea behind my 5-minute thing. I wanted to figure out how to do this and see if I could get better samples that weren't all black. And then I'd have a better chance of denoising that. But it turns out you start looking at this algorithm and asking questions like, how many times can you do this reject and reuse cycle and have it be useful? And how do you make this performance so that one pixel isn't trying 256 lights and one isn't trying one? Because that's not particularly useful on a GPU where you want your pixels to be coherent. And then how does this affect the sampling PDF? And well, my neighbor's light is probably really similar to mine. Why can't I borrow from that and save some cost? And so once I started thinking about this, this is, there was basically no limit to how many reject and retry cycles were useful, which was really surprising to me at the time. Now it's not so surprising. This is just Monte Carlo. And then it turned out that what we were doing was this RIS, this resampled importance sampling from Talbot, and the reuse from neighbors turned out to be the key question. And asking how to do that has really been what's occupied me for the next 6 years. Now, at this point, I want to point out that up until here, this has been me sort of pondering to myself and typing code and asking questions. But at this point, we got results that looked impressive enough that we actually started adding more people. So before it was my project, and after this it turned out to be other people's projects as well. And so the story stops just being mine here. And for those of you who are junior, it's sort of hard to let other people come in and join your project. You feel a little protective about it. But it's often a good thing because the more you share it with other people, the more good ideas you get and the broader your impact can be. And so after this point, everything is probably Marcus and Daci's idea or Benedict's idea rather than mine. And so expanding this beyond just me was really useful for ReSTIR. All right, so after solidifying the theory and removing some bias, we published our first ReSTIR paper in 2020. I think it's a really simple and elegant algorithm, although I also have a history of publishing things that I think are really simple and elegant, and other people think this is impossible to reproduce. So this might be one of my calling cards, but I think this is a really simple and elegant algorithm. All you're really doing here is saying, go pick a few sample lights and pick one. And then look in last frame and find where your pixel projected last frame, take the light from there, and pick between that one and the one you picked in step one. Then look at some spatial neighbors and pick between them and the one you picked in step two. And then shade with your one sample. That's the result of all these picks. So that's the algorithm. It's really simple in that sense. The question of how you do the picking can get a little hard, but that's all that's going on. And as you add more and more reuse, you get better and better results from this up here, which is naive one sample per pixel, down here to what we're getting with ReSTIR today. And so there's a huge improvement in quality. And so the algorithm isn't hard, but the statistical ideas behind them turn out to be newish, or newish to the computer graphics community, and somewhat unintuitive. And I'll get into that a little bit more later. Now, at this point, we had submitted our SIGGRAPH paper, and something new happened for me anyways. And that was, before this, in all my research, we'd had to go out and corral our product people and say, hey, we got this cool idea, maybe you should try it out. In this case, for ReSTIR, they came to us and said, when can we have it? Give it to us right now. And so we actually had a meeting with 30 people in Redmond about 2 weeks after we submitted this SIGGRAPH paper, with them saying, we want this now, how can we get involved? And so this was very different and actually led to some interesting things. So for instance, we had this paper demo that came out about the time our SIGGRAPH paper was announced that it had been accepted. And there's a couple things to notice here. One is this is noise-free. There's a denoiser working here. Before this, we had no denoiser for this sort of lighting, and we had no denoiser for ReSTIR that worked in a temporally stable way. So this was all because we had a bunch of developers, dev tech engineers, working on this to help us denoise this. And so we came up with a denoiser in a couple months because we had product engineers working on our research. And they also allowed us to get a lot better assets, crazy things like this NVIDIA logo, which turns out to be backwards, kind of amusingly, that's floating around in this scene. So they made this a lot more robust. I can look through here and still see where it's broken, but hopefully you can't. And they made the video production way better. So that was sort of an interesting and eye-opening new thing that happened to me with ReSTIR. But now we have well, I don't know if a problem, but we have competing interests here. We have a tricky thing. We now have our product engineers who want to make this into a product, and we want to push the research boundaries. And it turns out these can be a little bit competing goals. So for instance, our first SIGGRAPH paper had numbers in the 15 milliseconds to 50 millisecond range. And that's what we lovingly call SIGGRAPH interactive in the industry. Those are things where it's interactive in the SIGGRAPH paper when you get to take the whole frame for your algorithm. And that actually means we're about an order of magnitude off from being useful. So we need better performance to make this product ready. We need robustness in tricky cases. This particular scene is a Minecraft scene where there are 250,000 torches that are the only light. Well, there's actually an environment map here, but they're the only lighting other than the environment map. And in some cases, like these places where the arrows are pointing, exactly one torch is contributing the light. And so we don't need to find an aggregate lighting of all torches. We need to find the one torch that contributes in this pixel and use it. And that was not something ReSTIR was designed for. So we had to figure out how to solve these sorts of problems. We wanted to scale up and down in ray count. For future GPUs that have more rays, how do you deal with it? For things like console, which has fewer rays per pixel, how do you deal with that? And then integration into engines is really complicated. I can't tell you how complicated it is unless you've done it. So this is tricky. You come up with some research idea and then need to paste it on top of an engine that never had any idea that your algorithm could exist. On the other hand, really I think about research as trying to learn something, trying to ask a question and find out. It's following your curiosity. So I know I was reading a bunch of papers that cited the first ReSTIR paper, and a lot of them would say in their background section, but this is kind of limited because it's only applying to direct light. I was like, that's the wrong way to look at this. It's not, this is a limitation, but they only asked this question in this context. How can we take that and move that reuse to longer paths? So that was a question we wanted to ask, and we were asking behind the scenes. And in particular, how do you reuse in really high dimensional spaces? So direct lighting is sort of a 2D space that you're using samples over, reusing samples over. What if you have a 30-dimensional space and you have a point sample in that space? How do you reuse over that? How do you even think about it? How do you visualize that? Are samples only at points? And this is a really important question. Or can you take like samples over areas or regions or voxels? And what about bias? How do we understand that? And more importantly, how do we control it? So this image here on the left, I guess, is what ReSTIR looked like in my personal prototype before we started adding people on. And it was horribly, horribly biased. And on the right is the reference. And so what we wanted to do is have some control so you could sweep back and forth and control performance and bias, so you could say, well, I don't like that, but maybe this one here is good enough, the one in the middle. And so that's a better performance quality trade-off than somewhere else. And so which of these do you choose? Do you choose the production ones, or do you choose the research questions? Now, what I've discovered in 5 or 6 years since is that's actually the wrong question. The question you want to ask is, how do you manage the competing interests? How do you order them to help move both along in a productive way? And there's a reason for this. The better performance that the production wants helps you do your research. So if single bounce direct lighting takes 50 milliseconds, like it did in our first paper for some scenes, it's pretty hard to do a 30-dimensional or 10 bounce path trace on top of that if doing one bounce takes you 50 milliseconds. And so the faster performance that you need for productization opens up new venues for your research, and it allows you to ask more questions. And then the research actually helps the product, because, for instance, if you understand and control bias, that helps you make it more robust in a game engine. And that's something the game engineers are going to ask you for constantly. How do you make this more robust? And so asking some of these research questions is important in order to answer their concerns. And to help give you some specific ideas here of how we did this with ReSTIR, so at some point, NVIDIA decided we were going to, make Portal look better with RTX. And so we had a bunch of artists. And one of the things they did was they went and added little divots everywhere. These little golf ball-sized divots that were on all of the walls. I don't know why they did this, but they liked it. They're artists. That's what they do. And these alias like crazy, because there'll be subpixel, there'll be 4 of them within a pixel. And you try to reuse, and you're reusing between pixels, which are not really how you want to reuse in this case. And so these alias like crazy, they break the reuse and led to lots and lots and lots of complaints. Now, we didn't solve this for Portal with RTX before they shipped the game. We put some Band-Aids on it. But it forced us to ask how to handle subpixel detail. And that was the research question that was important. And now if we did Portal with RTX, we might solve it differently than we did then because we have better tools. And so this led to our area ReSTIR paper, and we were looking at subpixel detail, not just with normal maps, but also with hair, fur, and things like depth of field, which allows the geometry to change within the pixel because you have different perspectives. And the research also helps drive the product. So, we had direct lighting, which was pretty cool. But if you have a scene like this, you'd really kind of like to see through the glass of that spaceship. And this paper's kind of interesting because how it came about was Marcus came to me one day and said, Chris, ReSTIR doesn't work. I'm like, what do you mean? We're shipping it. What do you mean it doesn't work? It's like, it breaks. I don't know if we can ever guarantee convergence. I'm like, it'd be nice if we could. We're shipping it. It'd be nice if we could say something more about this. And so he went away and started thinking about this really deeply and came up with some amazing theory that sort of underlies this and allowed us to take ReSTIR from direct lighting up into mini bounce. And if he hadn't come to me and said it's broken, and it was broken, it just wasn't a case where no one would use it in practice. And what we discovered is if you don't know why yours breaks, and even the simplest cases, you can't think about how to expand it beyond that. And so that's what this paper really was doing, was solving this problem that no one would ever encounter in practice. But by solving it, we allowed ourselves to go up to higher dimensionality. And this now is shipping in the Zora demo, which you can go and download, and which allows you to do much more complicated reflections. It also does refractions, but not in Zora. And things like this microgeometry, you can get shadows from that, even though you're in the indirect lighting here of the shadow of the sun. So the research also drives the future product directions. Now, the key here is don't be afraid of product and go talk to the people who are building them. You have to be careful, though, because the very first question almost every engineer asked me about ReSTIR was, can you do it in a world-space grid? And I was pretty fed up with this question because it seems to me to be the wrong question. Because one of the challenges here is if you have a world-space grid like this here, those are not point samples. Those are area samples. And until we came up with area ReSTIR, we had no idea how to deal with area samples. And so every time an engineer would ask me, well, can't you just do this in a world-space grid? I would say, yeah, but we can't guarantee anything about it. It might blow up after 2 frames. And often it did. And they'd come and ask me, why is it blowing up? I'm like, we don't understand that part of the math yet. You have to give us time. Oops. But the pressure of getting these questions asked forces you to prioritize your research in a certain way. And so by having people bringing this question up, it was clear that it was a very important question. And we needed to ask, how does ReSTIR integrate over regions rather than points? But this also applies to other things like motion, blur, depth of field, anti-aliasing, things like that. And by By keeping in contact with product, it ensures and builds demand. Well, it ensures there is demand for your work, because if you solve a problem that no one cares about, no one's going to care about it. But if you solve a problem that is really important, it builds this demand for your research once you're done with it, and that's really valuable. And so a question that you should ask is, how do you do this, particularly if you're not in industry now? And the right answer to this is talk to all of your friends in industry, of whom many of them are here in this room. So you should ask what problems are important to people in actual production. Not that you have to solve those directly, but you need to think about what research questions they actually, lead to. All right, so now I want to take a step in a different direction and ask what ReSTIR has taught us, or at least has taught me. So the first thing is that lighting really is locally smooth, for some definition of local. And this is often a quoted rationale. I think I quoted this in my PhD dissertation 20 years ago. So for denoising, for image filtering, image processing, irradiance volumes and caches, image-based rendering, view interpolation, often one of the rationales quoted is, well, this lighting signal is actually quite well behaved, it's smooth, and so we can interpolate colors in this way. Now, the thing that we've sort of learned here is it's also true for high-dimensional path spaces. This space is also pretty smooth in general. And this is hard to actually think about, but if you consider that the color that you're interpolating with the denoiser is just a projection in some way, a projection from this 30-dimensional path space down into color space. Of course, if the color space is smooth, then that 30-dimensional space also has to be somewhat smooth in order for the projection to give you a smooth result. So it's not obvious when you start trying to think about and visualize the 30-dimensional space. But if you think, well, it's projecting down to something smooth, it seems logical that that high-dimensional space is also smooth. And this has some interesting implications that were a little counterintuitive to me. But some dimensions will have discontinuities, but not all of them will. And so, for instance, on the left here is our ReSTIR PT, and we're looking at multi-bounce glass path through wine glasses with some depth of field, some pretty strong depth of field. And with ReSTIR PT, you get a lot of noise. ReSTIR PT was using a point sample. And then we went to a higher dimensional sample through where we were integrating over the pixel and the lens. And suddenly we got much better reuse. And the idea here is that if you think about, you have some discontinuity where you can't move, you can't reuse over this boundary. But if you have an extra dimension, you can go up and over and around and reuse. And so in this case, what's happening is you've got the glass, and the throughput is this Dirac function. You have one or two dimensions, one for reflection, one for refraction, one directions that you get throughput, and no other direction gives you any valid throughput. But if you can move the position on the lens and the pixel, you can actually move the ray a little bit and still get reuse along this glass. And so ReSTIR can extract that and pull that out if you give it a higher dimensional sample. If you leave it in ReSTIR PT at a lower dimensional, you can't do that reuse. And so that's really interesting. That says even glass is locally smooth in some dimension. Another thing that ReSTIR has taught us, and this is really important, this is really leading a lot of our research right now, is never throw samples away unless they're truly useless. So reservoirs give on the order of 50x multiplier. Sometimes it's 20, sometimes it's 100. If you have a reservoir, it's that much better than a single sample. So if you discard a reservoir, you're throwing away a ton. Your quality degrades instantly when you discard a reservoir. So you don't want to do that, ever. If you can keep that reservoir around, you saved a 20 or 50x multiplier in that pixel. So that's really important. And so that's really what's going on here as well, is that with ReSTIR PT, we were discarding a lot because in this particular case, we would have some foliage on the grass, and this is all tessellated at some extremely ridiculously high level. And as soon as you move just a little bit with ReSTIR PT, it would discard it and say, the normal's pointing in the wrong direction, I can't reuse here, I don't know what to do. Or along the lighting, the indirect lighting up on top of, above the door, or even around the glass on the window, ReSTIR PT didn't have any idea how to reuse, and so it discarded it, said, I don't know how to reuse this thing, throw it away. But if we were able to keep it in this higher dimensional sample, with this higher dimensional sample, we get better reuse there because we're keeping the samples around longer. We get to amortize them more. So this is really important. Don't throw your samples away unless they're truly useless. And this seems like an algorithmic problem with ReSTIR, but you can also treat it as a research question. So what happened in the basic ReSTIR was you'd take your current pixel in your current frame, you'd back project it to the prior frame, and it would land somewhere in the prior frame pixel. And then you'd say, can I reuse the pixel at the center of that pixel it fell into? The sample, yeah. Can I reuse the circle at the star? And it might be that you were unable to reuse that for various reasons. Maybe the normals were different, the depths were different, the materials were different, something was different, and you'd throw it away. And so this was a problem for the basic ReSTIR. So then we came up with this area ReSTIR, where you would take the footprint and back project the footprint into the prior frame, and it covered some part of a 2x2 region. And then you'd move all the 4 samples from that 2x2 region into your footprint using a shift map. And so you'd have 4 choices for reuse. And that was better than 1, but maybe all 4 of those had different geometry, normal materials or something. And so still sometimes you couldn't reuse. So we actually have an upcoming SIGGRAPH paper which turns this around and says, rather than take and back project to the prior frame, why not forward project your sample to the current frame? And now we have a star in the current frame, but because we can use over a pixel with this area ReSTIR formulation, we now get direct reuse from that. We can guarantee it's valid in the current pixel unless it gets occluded because something blocked it. That's the only reason we couldn't reuse this. So before we were potentially throwing away due to normal or depth or material or some other property. Now we always reuse unless it's simply not visible anymore. And so that gives us this result comparing area ReSTIR to the splatting. I star the area ReSTIR because area ReSTIR didn't actually do motion blur. And so this was sort of a naive addition to area ReSTIR to do that. But if you do splatting, you get to reuse a lot of samples, like down on the ground here, there's a lot more red. And so there's just much more reuse here. So that's something we've learned, never throw samples away. Another thing is shift mapping and MIS, multiple important sampling, I think are now required rendering knowledge. They're not optional advanced topics. These are often things that would be taught at the very last minute, if ever, in your rendering course. And I think they're now sort of required. And the reason why is, let's say you want to reuse samples. And now, pixels are different domains. And they're different integration domains. They're different problems. And you need to have all of your samples in a consistent domain in order to be able to reuse them all together. I sort of think this like asking the question, how many grams are in a meter? It doesn't make sense. And this is sort of what you're doing with ReSTIR when you reuse between different domains. You're like, it doesn't even make sense to reuse that sample over here, unless you find some way to make them play nice together, and that's what the shift map is. The shift map moves the sample from one domain to another, so you have to have it, otherwise you're asking how many grams are in a meter. And because each pixel is its own estimator, estimating its own different integral, if you're going to borrow the samples, you're using different estimators, and that's what MIS is for. That's the standard reason you would use MIS, is to take multiple different estimators and turn them into one. And I'd like sort of a 1D illustrative example of this. So let's say this is a non-analytic function here, and you want to integrate it in 1D. one thing you could do is you could pick some samples uniformly across the domain, and that gives you this yellow importance sampling line, and you pick samples according to the yellow line and then reevaluate them based on the evaluation of this curve. But that's going to give you somewhat noisy results. So you could pick a more important or a more complex importance sampling function like this one, and that one might give you better results, less noise. But an interesting question is, could you use this purple curve to importance sample this value? And this purple curve is interesting because it's very, very close to the curve that you want, but it doesn't cover the whole domain. So what do you do in this red region where you have this really good purple, but it doesn't cover your domain? If you use it like this, you're going to get a biased result because you're not ever going to pick samples in the red region. And so an interesting question is, can you use a function like this to integrate? And it turns out that the answer is yes, but you have to combine it with another function, like this other yellow importance sampling function. And then what you need to do is you need to have MIS weights to combine them together. So if you pick a sample in this rightmost region that was red, the MIS weights of the yellow will be 1. And if you pick over here, it will weight hopefully more towards the purple one. So that's really what ReSTIR is doing in a 30-dimensional space, projected down into 1D. That's what's going on. So the ReSTIR shift maps from one domain to another. That's that figures out what the coverage of the purple one is in the current pixel. And MIS combines them together, so it allows you to reuse this. And the smaller this green region is, the better ReSTIR does, because you're reusing a really good purple importance sampling function for your current pixel. And if you have any of this green region that's not covered by a yellow sample, you get bias. All right, another thing I've learned is bias is important in real-time rendering, or really unbiased algorithms are important to think about. And this is a long-running argument in real time. Do we want unbiased algorithms, or do we just want it to look good? And I used to be on the just want it to look good camp, and I've changed my mind over the past 5 years. And it turns out that gamers care about bias, they just call it something else. They'll complain about ghosting or blur or smearing or halos or flickering. And these sorts of problems are one of the reasons there's a lot of game developers that absolutely hate TAA. Because what TAA is doing is it's introducing all of this bias and doesn't provide you any way to control that bias in a meaningful way. And so you have to hack things in to make it work. And what you're trying to do is debias TAA. And wouldn't it be nice if you just had an unbiased way of reusing temporally and spatially, which ReSTIR gives you? So what we want to be able to do is control the bias. And so we want to understand how it arises and avoid, and one of the reasons we want to do this is you end up combining lots of algorithms together in a renderer. And if you don't understand bias in your algorithm, when you combine it with another algorithm that's also biased, you don't know if it's going to explode in your face. So what you really like to do is have things unbiased, or at least understand where the bias is coming from, so when you combine them together, you understand whether they're going to work together in a nice way or not. So this is just some examples showing biased and unbiased rendering with ReSTIR. And by selectively adding bias back in, you can often add performance back, even though the unbiased algorithm is somewhat expensive. Now, understanding bias has allowed us to push reuse a lot farther than I ever thought we would be able to do. So the original ReSTIR GI is unbiased if you follow all of its assumptions. And the assumptions are everything in the scene is diffuse. It turns out that artists want to break this assumption almost immediately. You give them an algorithm that gives you great rendering with all diffuse surfaces. They're like, well, can I just put a little bit of gloss in there? That's almost the first thing they ask. And what turns out with ReSTIR GI is if you start breaking the assumptions, over time, this bias adds up and grows, and suddenly you start having glowing parts of your carousel as it rotates around. And this was after like 20 or 30 rotations of the carousel. So it wasn't immediate. It was just over time, suddenly it started glowing. Whereas our more recent ReSTIR work is way more stable. You can let it go to lunch, and your carousel will still be normal looking, not glowing. All right, so where do we go from here? And I want to say there's actually a lot of directions, and we're certainly not doing them all. To sort of motivate this, to motivate this, I want to start off by saying that modern ray tracers generate lots of rays. Certainly our research ones, maybe not all the game ones do, but if you think about 10, 20, or 40 pixels or rays per pixel, you can definitely do that in a research ray tracer in a game, budget. And so that gives you something like 80 million rays per frame, or maybe 5 billion rays per second. That's a lot of that's a really dense sampling of your scene. So here I've drawn a bunch of paths, really stupid paths that just sort of wiggle out. But these are a bunch of bounces in these paths. And if you think about that, this gives you lots of potential combinations for how to reuse these paths by combining one bit with another. And we're not doing this in ReSTIR today. We're sort of combining a very small select few. And so if you think about how dense this sampling is of our scene, where we're tracing rays, if we could reuse all of them in arbitrary ways, we'd have a lot better results than we do now. And this is sort of what motivates me and inspires me to go further. And so what we're really doing is we're discretely sampling the path space and reusing within it. And this is actually not all that different from what we do, say, with environment map sampling. You never think about an environment and say, well, I'm only reusing from one of the 4096 by 2048 samples in my HDR map. And think, well, I really should be using from the continuous space of theta phi over this, and how do I do that? No one asks that. They just download from Polyhaven whatever HDR they want to use at whatever resolution they care about, and that's what they use. So maybe the discrete, how densely sampled does a discrete path space have to be? Maybe with 5 billion rays, we're dense enough. And so then the question is just how do we reuse them? And that's really what ReSTIR's trying to ask, but we haven't gotten, I don't think we squeezed even half the juice out of this. So once you suggest that you might have your samples dense enough, you need to ask, how do you identify which ones to reuse? And so that's the next question. How do we pick good samples for reuse? And what I'd say right now is, I think we've done a pretty good job of doing temporal reuse. We can reuse in ReSTIR temporally really, really well. And I've often said to other people, temporal reuse is more important than spatial. And you can sort of see what I mean in these 4 images. You've got naive sampling, spatial only reuse, temporally only reuse, and then both. And you get most of your quality here with temporal. But maybe that just means we're doing bad spatial reuse. And it turns out that the spatial reuse we're using in ReSTIR now hasn't changed since the Bitterly et al. Paper. And in that paper, we didn't actually do a very good job of selecting how to do spatial reuse. We just said, well, if we're at this circle pixel in the center, let's pick a 30 pixel radius and randomly pick some pixel in that radius. And that's what we've been using ever since. I would argue you could think of a lot more things that are useful, a lot better than that. And now that we have better tools for reuse and understanding the theory of reuse, I think we can actually ask some interesting questions here without doing an exhaustive search over some large region, or if we're doing a lot of expensive shifts. And what's beyond reuse? So imagining that you have this dense space and you reuse a lot, can you perturb some of the samples just a little bit? And this might be related to MCMC and mutation, or path guiding. How do you take these samples and allow you to generate some new ones that are similar to them but not the same? And this can help you reduce some of the correlations in ReSTIR. I think this is a really interesting direction. Another problem that's actually a huge problem is how do you play nice with denoisers? And really the question here is who gets to add correlations to the output image? So modern denoisers make a lot of assumptions like noise-free G buffers, or they assume white noise input. And most people don't think about these denoisers, especially when they're reviewing papers. They just say, haven't you tried this with a denoiser? And they didn't ask, will a denoiser work on this sample? Does it fit with the assumptions of the denoiser? And some questions to think about is, if you pass a rendering signal to a denoiser and it gives you a bad result, whose fault is that? Is it the rendering algorithm, or is it the denoiser? Or might it be both? Or the answer might change depending on what the assumptions of the denoiser are and what your renderer are. And why is it okay for a denoiser to add correlation to an image, but it's not okay for your renderer to add correlation? That's an interesting question. Is the G buffer the right latent space? And I'm sort of incorrectly using the word latent space here, but I'm doing it on purpose. Is it the right latent space to communicate with the denoiser, or should you have some sparser representation? Do the denoiser and renderer need to be coupled? Can the denoiser handle general input frequencies? These are interesting questions. And it's interesting to point out that ReSTIR doesn't even have consistent noise characteristics across an entire image. So where you have discontinuities, suddenly you have higher noise. And it turns out modern denoisers treat these regions differently than the other parts of the image. And so your denoiser actually changes behavior over this image, which is unfortunate. Better use in dynamic motion. Mappings between pixels are more difficult under motion. And you've got problems with, well, in this case, the video is showing no motion at first and then motion. And the reuse is much better when it's static, but when it moves, you lose a lot of quality. And so how do we improve that? How do we avoid discarding reservoirs once you start moving? And what's the answer to this? Is it stable ray tracing? Is it something else? I don't know. And what does ReSTIR mean for offline rendering? And I don't have a build on this one because honestly, I don't know. Someone who has a good idea is welcome to try this out here. All right, so let's wrap up. ReSTIR is about focusing on sample reuse. And it's not new, but reusing samples is really important, especially as we go into a place where Moore's law is ending. And what ReSTIR is the combination of resampled importance sampling with weighted reservoir sampling, and that's really changed the game. With Moore's law dying or dead, we need new ways of improving quality, and I think reuse might be the way. Its speed gives sample reuse new applications. I used to facetiously say the solution to problems in ReSTIR was more ReSTIR, because reuse can solve some of these quality problems just by iteratively applying the crank one more time. For me, reuse is fascinating. We never get it perfect, so we always have more ways to say, well, here's another bucket that we could potentially reuse these samples. And each time we do, we get a huge improvement in quality. But yet we already have a useful algorithm, and it's shipping today in many places. So with that, I don't know if I left any time for questions, but.
Yeah, let's thank Chris. We'll make some time for questions, so yeah, please.
Hi, that's all really interesting. I had a quick clarification. Yes, I had a quick clarification question about some of the resampling, especially onto your point of like there's all these many crossing over ways that you can use resamples rather than just in the neighborhood. And I think you already answered this because I can't imagine it being like as precise. Is the idea in mind for reusing these samples that like some of them are just kind of close enough to what you wanted to reuse? So you had, for example, you had two rays in two completely different positions on the screen, X all the way here, X all the way here, but both of their secondary balances went to about the same area. Is the idea that it's like, oh, well, these are within an inch of each other. This should count as the sample reuse?
The answer to this question is sort of, there's multiple answers.
Okay.
So in one sense, yes, that's what I'm suggesting is this similarity allows you to reuse. But another thing to think about is we're really reusing distributions, stochastic distributions of samples. And so as long as these distributions are partially valid to our current pixel, then when we've picked a sample in one distribution, that is valid wherever that distribution is valid. And if it's valid, what we're doing in Monte Carlo sampling is we want to pick all of the samples in the distribution so we cover the domain. So what we want is we want to make sure we have as many samples as possible within the valid range of distribution, which includes those that are not particularly relevant. And so what we're actually doing here is we've sampled this PDF space, and we're reusing within this PDF space, and those samples are valid there. Whether, I mean, another way to think about this is if you have paths, right? And you could reuse the 7th bounce and on of your path. What does that mean? How does that affect the first 5 or 6 bounces? Well, as long as you can see that sample on at the 7th vertex, you can reuse it. So it might not be exactly the one you would have picked randomly from your 6th vertex, but as long as you can see it, it's relevant, and it contributes light. And so you should at some point sample it, and well, we already have the sample laying around, might as well use it. Is that?
Approximately. I had one more, actually, and this was, again, one that I might know the answer to, but also just wanted to check in.
Right.
So you have this resampling process where you just like go in, and the initial example, this light is going to be obscured, it's going to lead to a black pixel. Let's try to pick the next one.
Yeah.
Can that, at that point, be parallelized, or would that not be worth it? It would be better to just to do 2 samples instead of that.
Well, you could certainly parallelize there.
Would it be worth it to, I mean? Because that kind of destroys the point of the amortization and and that now you're using extra threads that you could have been using on their own samples. I'm just wondering about that.
Yeah, well, I mean, you're asking if I'd made a different choice on optimization 5 years ago, where would I be today? Oh. I mean, is a different way of phrasing your question. And the answer is, I think you could optimize it for performance the way that you're suggesting. Whether that would lead to something interesting or not, I don't know.
Well, thank you.
Yeah, we're looking back at that carnival scene with like the balloon, and you saw like it ended up glowing a lot. I'm curious, why did you think that happened? Is it because it's like the samples started like stacking up on each other, and it caused like the light become wider every time? Or?
Well, so probably what's going on in this scene, which is the same scene, which is why I moved to it. Probably what's going on there is that there are some surfaces with clear coat, which are delta functions. Okay. And delta functions have zeros a lot of places and are very difficult to reuse samples across. Okay. And probably what's going on is every now and then there's a sample that is biased because of this delta function, and they slowly accumulate and blow up. Now, if mentally you don't understand where the bias and you can't visualize how bias shows up in ReSTIR, it's hard to follow that chain of logic. So I understand if that doesn't make sense, but that's where I believe it's coming from.
I think it does.
Okay.
Yeah.
Let's thank Chris again, and yeah.
Thanks.